is to try to complete, not try, we had to complete chapter 9 because we've already spent 2 weeks on it already. It's parts of 2 weeks. So that we can start the refrigeration next week. We'll have to go through the exam again. What did you guys think of the exam? Was it hard or easy?
I don't remember.
You don't remember?
Yeah, last week was just this onslaught.
It was,
Which exam?
which exam? Yeah, which? Yeah, that's true.
There were a couple, like I studied all the examples pretty much in 7 and 8.
Yeah.
Hardcore, I knew them, but then there were a couple differences between your problems and some of the examples, and I couldn't figure out how to bridge the gap.
I think there was just some wording that I like the way the question.
One of the problems was exactly example 1 in that vapor power. It's the Rankine cycle. It's identical.
8-1, right?
Yeah.
Yeah.
I know 21.
It was the.
It's identical to that one. I mean, I just changed the pressures, and of course, I'm not going to give you the same pressure. So essentially, finding 4 H's and then everything is the thing. That's why if you get an H that is wrong, you're going to get taxed a little bit. Another exergy problem was a homework problem. I think that I just changed the numbers on. Probably just noticed that. It's a homework problem.
Yeah.
I just changed some numbers, that's all. And then the other one was just what is an exergy change. So I really thought it was going to be good. I'm not saying it was bad, you know.
But it wasn't good.
But I was hoping it would have. I was hoping for better, but hey, it is what it is. So it's a good thing I don't grade severely. So if you get something, you know, a wrong approach. You know, one thing that made me sad though, the first problem, when I said the rigid, and I said it before, remember we saw it so many times. When we say rigid container, what do we mean? Constant volume. But then people in the TV diagram, they go, ooh, state 1 is here, state 2 is there. You know, it's obviously it's changing volume, which does not make sense. It's got to be moving vertically up and down. So obviously, if you start with a wrong footing, the whole thing is wrong, right? But you know, but you got a lot of points, anyways. Just all right. So let's go through that, and then we'll go through the illustration. Just see if I can get it here.
Was that the first problem?
And do you want to exam now or later?
Now.
Never fails.
Answer always no.
All right, let's see.
Right on top. No.
Means good or means bad?
Oh, that's. I'll take that all day.
Well, of course you would. I had to do it twice to get you there.
Reverse alphabetically.
Twice.
Alphabetical remembers the movie name.
When you put just a red, like just a red, like that, what does that mean?
That is okay.
Oh,
Yeah.
was good enough? Okay.
Yeah, good enough.
Goodness.
How did I still? Oh, I still made it go. I had it up and down.
There you go. All right, let's take a quick look here.
Yeah.
So you had 3 problems worth 10 points each, by the way, so you just know. And then whatever points you get off is usually what I deem necessary for the mistake. Usually should be more, but it's, you know, you always get partial credit. The only time you don't get partial credit is if you leave everything blank. Give me no choice, okay? But let's just take a look at what's going on in here. In the first, you had 2 problems, and the way I decided to do this is I gave you one on exergy change for a closed system. The other one is for an open system. You know, I kept it to the minimum. And the first one, which had a rigid container filled with refrigerant vapor, initially at 1 bar at 30 degrees, and the vapor is cooled until the temperature becomes 36, and there is no work during the process. And I said, show the process on an annotated TV diagram. This is what I was hoping that you would probably do, you know. It's a TV diagram. First of all, because state 1 is defined by what? Pressure and temperature, you should show that it is actually in a superheated region. You know, you gotta be explicit. Where am I? So where am I is by obviously showing the dome and showing kind of a pressure line, and you say state 1 is here. And then what I was hoping to see is that state 2, you just come down. Remember, as you come down, you either are still in the superheated, or maybe you hit the saturated, or maybe you're below. The way you do that is by going back to the temperature here at minus 36, and state 2 is defined by what? You need 2 properties, right? The temperature is given, so what is the other properties? The specific volume associated with first, okay? When you do that, you know that specific volume, you check with the VGN. Remember what we've learned in the ENGR 355. You check with the VG and VF of this state, and you find that your V is actually in between. That means you are under the dome. And anytime you're under the dome, you have to calculate what? Quality. I mean, that's the same story. And so the first one was to show this on a TV diagram, and then determine the heat transfer. Well, it's a closed system, right? The heat transfer is only a function of what? You have to apply the first law of thermodynamics, right? So here for B, for the process V1 is V2. From table A12 at 0.1 and 30, I read what V1 is, S1 is, and U1 is. I read the S's because I need to do the exergy, otherwise I wouldn't need it. And then from table A10 at minus 36, I read VF is this, VG is that. If you compare here your V, you know that you are in between, right? That means you have to have a certain quality, which happens to be approximately 0.8213. Now this quality will allow me to do what? It will allow me to find U2 and S2, which I need for the next questions. To find what the heat transfer is, I just write the first law of thermodynamics. Remember, that's what I said. Anytime you have a closed system, that's what you do. Q minus W, there is no work because it's a rigid system, is equal to delta U because this is neglected. So Q is simply M times delta U, and which is U2 minus U1, and it's minus 83.92. Okay? Now to find the exergy or the change in specific exergy, now I need to clear a couple of things. We learned in chapter 7 how to calculate the exergy of state. That's when you compare that to U0, T0, stuff like that, you know. In fact, it's U minus U0 minus P, V minus V0, etc. But then we also learned how to do exergy change between the 2 states. That's E2 minus E1, okay? So in this case, obviously the change in exergy, we've probably seen this equation before. It's U2 minus U1 plus V naught, V2 minus V1, S2 minus S1. But because this is a rigid container, this is always going to be 0. Now we have all the values done. Okay? Change in exergy is equal to plus 12.15, and we are done with the problem. Okay? So it combines elements of the first law of thermodynamics and the change in exergy equation. Now when we go to the second one is sort of similar, but it shows you it gives you water vapor, which is nice, at 6 megapascals and 500 degrees, which if you look at the tables, you find that you are actually in a superheated state. It enters an insulated turbine operating at steady state here. And so it enters at this state and exits at this state, which is what? At saturated vapor at 0.7. So the two states are well defined, you know. The effects of motion and gravity can be neglected. Great, PE and delta KE are 0. Determine the work developed and the exergy destruction, okay? So there are actually two questions in one. I didn't want to break them into two. But finding the work, just like when you are being asked to find what is the heat or what is the work, in the most cases you have to use the first law of thermodynamics, you know? In the previous one we used it for a closed system. In this one, if you apply it to an open system, what would it be? Remember in a vapor power cycle, whenever we go over a turbine, what do we say the work is equal to? It's H1 minus H2. It's just delta H, the difference in the two, if you don't want to start from scratch. Okay? So here we're coming in, obviously coming at 6 megapascals and ending right there. So coming back in here, reducing the mass and energy rate balances, you know, the work is H1 minus H2, so it's 762.2 kilojoules per kilogram. The second question is, what is the exergy destruction? So you use the equation for exergy destruction. The equation for exergy destruction is really what I have here at the bottom. Don't look at this stuff in here. You could start this in one line. You could finish this problem right there. You know, this equation, right? Remember that it's an insulated turbine, so this term is 0, right? The work we just calculated in the previous slide, 762.2, right? And then plus M, EF1 minus EF2, which is M dot H1 minus H2 minus T naught S1 minus S2 minus E destruction, okay? That's essentially what this equation is all about. And when you plug in the numbers, you find that the destruction is 179.82 kilojoules per kilogram. So again, exergy for closed, exergy for open. And the third problem is the one that I was mentioning before is again very identical to all the problems we talked about. I think I just fiddled around with some pressures here and maybe mass flow rate. I don't remember what I did, but in any case, and I broke those equations very carefully here, the questions, to come up with drawing the sketch to make sure that we typically do them exactly the way we are supposed to be doing them, right? So you get, this is the physical state, the numbers need to be shown, and then the TS diagram, and what are the enthalpies of the four states, okay? That's really where we should be, okay? If you find all those enthalpies, you should not have any problems. Obviously, if you get one or two wrong, it affects the other ones, you know, but that's really, most of the weight is really identifying the states correctly. Enthalpies of the different states. State 1 obviously is saturated vapor. So at 200 bars, saturated vapor, that's a no-brainer what H1 is supposed to be. Because it is the start of an isotropic process, we need the value of S1. And very critical that we read the correct value of S1 because it's going to, otherwise we're not going to get the right quality in 2. And then at 2, you know what the pressure here is, it's 10 kilopascals. Some of you, I think, use 10 megapascals. Somebody did that. I don't know who. So this is obviously not mega. It changes things. Point one, S2 is equal to S1, so the state number 2 is well defined. You compute the quality, which happens to be 57%, and then this allows you to calculate the value of H2. Now H3 you don't have to do much because it's just HF. Okay? State 3 is just HF, it's saturated liquid. And then H4, I wanted you to use this approximation equation. Remember, H4 is always H3 plus the specific volume at 3 times the change in pressures, okay? With the appropriate, obviously, unit conversions. And then you find 212.02. Once you have those 4 H's, then the rest of it is just plug and chug, I think, as they say, right? Work on the net work is the work produced by the turbine minus the work used up by the pump. And it should be about 1.083 10 to the power of 5 kilowatts. And for the steam passing through the boiler, you know, H1 minus H4 times m dot. The efficiency is the work produced divided by Hn, should be roughly 37.9%. And then for the control volume enclosing the condenser, now, mass of the cold water, see what happens in the condenser, just so we know what's going on in here. Anytime you come out of the turbine, remember that's state number 1, right? State number 2, and then you go back to the condenser here and state number 3, right? So what's the role of the condenser?
Take heat out.
Take the heat out, okay. So what is the heat out equal to? As a function of, if you have a mass flow rate of m dot, of the working fluid going through it. It's m dot times H2 minus H3, right? Without thinking, right? But then, we always say Q out without saying really how Q out is being taken out. But if you are getting some cold fluid coming in like this, this is the mass flow rate of the cold water, okay? So this heat has to equal what? Well, it's the mass flow rate of the cold water times, I think I gave you some delta T of the cold water, didn't I?
16.
Yeah. So times C times delta T of the cold water. What C? Because there's no CV or CP, right? This is 4.179, whatever the C of the value is. This is known, 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 and you're supposed to just find what this one is based on, that's where this equation comes from, which is m dot H2 minus H3 divided by C of the water times delta T of the cold water, you know, where this is, you know, from any table. Usually find that that's 4.18 to be done close.
I got a question on so
Yes.
that formula that you used is on the bottom. You got CW and then
Yes.
deltas. That's not the same formula in the example. On the bottom they have HCW out minus HCW in. So I had a hard time trying to figure out what that was. So I had no idea how to do the second part.
The second part.
Well, this last part of the problem, I was like, I'll just throw in my best guess on what those two variables are.
Was it close?
My answer? No,
That's where I got stopped.
not even close.
That problem 8-1, right?
Yeah.
Yeah.
Let me see if it's the same thing here. If cold water enters the condenser at 15 and enters exit 35. That means in this case it's
That's
Oh.
what that problem.
Oh, okay, so I guess the difference is, the difference in this problem because of between the one that I gave and this one has very specific temperatures of the fluid coming in and specific temperature of the fluid going out. In that case, obviously, you can go and find what is the, in the tables, you know, because you know that here what you're given is 16, 16. So you could be coming in at 36 and leaving it at, no, I mean, it's a
Any
difference.
delta.
Yeah, I mean, you can coming in at 20 and going back at 36, for example, or 30 and coming back at 46. So when you have a change in temperature, this is for any substance that is incompressible, just like a solid, right? That's what, at least that's what I was thinking in my head. Q is equal to mc delta T. When it's the temperature that is given. Now, if somebody says you have, you're coming in at a very specific temperature, I guess that's my answer to why this is slightly different. Not that much. But if you got dinged on that one, you probably didn't get dinged very much at all. At all, at all. So that's where we are. And in the next exam, you're supposed to know how to analyze you guys probably know, Otto cycle, diesel cycle. Probably something else.
Is it just gonna be chapter 9? No, 10. 9 and 10?
It's not gonna be 10 at all. I
Just
don't think
9?
I'm gonna do 10. It's probably just gonna be, it's just gonna be 9. Just gonna be 9, so it's pretty, it's gonna be again, you know, identical, not to the letter, but, you know, come on. But it's gonna be really identical problems. How to analyze an Otto cycle, a diesel cycle, and probably a, what's the next one? Not Rankine, Brighton. Brighton. 3 problems, so you'll probably be given a little bit more time. But I think it's targeted thing, so, you know, if you do those problems, if you do them, you should not have any problem. And the table is going to be really nice because it's only one table. Table 22. So no excuses for the second one.
Is it gonna be open book also?
It's going to be open book too. So, you know, I'm trying to make it as painless as possible this year, this term. Not that I didn't do it last term, but this term I did that, and in fluids, a lot of people did good. I don't know. I may have to ramp up my thing for fluids.
No.
We did too good.
All right.
Can you just grade us super hard?
Oh,
I don't like to
this
grade.
period
I
here.
don't like to grade super hard. I mean, it's. I mean, you probably look at your copies and go like, really? Did I get this? Oh, he was generous. Right?
It was the cold medicine last week, right?
Yeah, that's it. Last night, yeah, I was messed up last week. I was not good at all. All right, so. Oh, come on.
And then if I hadn't been trying to figure out what's the matter.
Okay, I don't remember where we stopped last time, but I think we finished.
Where did you stop last time?
What's that?
We are
9.7.
at
9.7? Okay.
9.7, right at the beginning.
Beginning of a 9.7?
Yes.
Cool. 9.6, 9.7, okay. Before we do 9.7, I just want to draw something from here. Just how an ideal,
Is this the third cycle we really need to know?
yes, this is the third one. So auto diesel auto diesel bracket. So if you study this example, you can reproduce this. So what do we have here? One, two, three. So this is the cube of pound. Okay, so what I've just drawn on the board is really the ideal Brayton cycle, right? Which is composed obviously of two isentropic processes and then two constant pressure processes. Okay? And I remember the Brayton cycle. Here, state number one is always the entrance to the compressor. So you compress the air, you replace the combustion by just saying, hey, I'm just adding some heat. Then you expand through the turbine, you produce some work, and then you extract the remainder of heat, and then you finish the cycle again. All right? Now let me go back. I think for all practical purposes, as far as the air standard Brayton cycle is done, we have covered that, okay? So I'm gonna jump to section 9.7, just to mention briefly, just as we did for the vapor power cycles, how do we increase the efficiency? But we're not gonna go through the darn examples all over again, okay? Because the problems become much more involved in the sense that instead of figuring out how many states here, 1, 2, 3, 4, right? We would be doing like 6 or 7, and then I think it's just, okay. So, regenerative gas turbines. In gas turbines, you probably know that all the combustion air, the combustion products, that are created have really high temperatures. And they are typically just exhausted out to the air, like this. So, do you agree that they have a high exergy just before being dumped in the air? I mean,
The temperature's really high.
it is high. I mean, it's just coming out of the combustion. But by the time they mix in the air, that exergy, remember, goes out, right? Dissipates. Now, people go like, hey, why don't we look at the hot turbine exhaust gases because they have high potential for use. Remember, exergy is the economic value of energy, right?
So I got a quick question. So chapter 9, even though it's gas, it's specific to combustion.
Yes.
So the exhaust gas is coming out of a combustion turbine.
Yes.
What combusts is the oxygen. So when we're saying, okay, so there's a lot of exergy there just because it's hot?
Yeah, just by virtue
Just
of its
because it's
temperature.
hot.
Yeah.
Even though we've just burnt as much oxygen as we could out of there?
Yeah,
It's still
because
got a whole, okay.
Yeah, because remember, in engineering, we're not talking about the combustion itself. The combustion has been replaced by what from our analysis? By heat. We just call it heat. So for us,
So
it's-
the energy just.
yeah,
Okay,
exactly.
I'm following.
So as long as something comes out as hot, it has value. It is heat because it can theoretically run another
Yeah, no, that makes sense.
another thing.
Just turn the-
So it says here, the hot turbine that would, why that would be irrevocably lost where the gas discarded directly to the surrounding. So the way they do this is they use what we call a regenerator. That's why we call this regenerative gas turbines. One way of utilizing this potential is by means of a heat exchanger called a regenerator, which allows the air exiting the compressor. See, what happens to the air going down the compressor? It gets in here, and then there is heat that gets added to it, right? So, and then you go like, man, this stuff that I'm rejecting here is already hot, right? Why don't I use it to preheat the air that is coming out of this before getting into the combustion fuel, right? So in other words, you're not going to increase its temperature from here to here, but maybe just from here to here. And then you get some savings, essentially, into the energy. It says, which allows the air exiting the compressor to be preheated before entering the combustor here, thereby reducing the amount of fuel that must be burned in the compressor. So how does this thing, how is that thing going to look like? Well, you're coming out of the combustor here, coming into the compressor. Compressor, usually from 2, you go directly to the turbine, right? But now instead of doing that, from 2, you go to the, not the turbine, but to the combustor. But instead of going through there, you see, what comes out of the turbine, which are hot gases, are rerouted, instead of just rerouting to the atmosphere, you reroute them through what? A heat exchanger. This is again, haven't learned this yet, but this is a counterflow heat exchanger because the two fluids are going in opposite directions, and that's usually the better efficient heat exchanger. So before going out, what is happening here, you think? The hot gases, when they come out, they will be cooler, right? But in the process, they lost their heat to the gas that is coming out of the compressor. So the temperature at X is obviously going to be higher at 2, right? So here, the heat added per unit mass will be what? From enthalpy considerations, it's going to be simply H3 minus HX instead of H3 minus H2. Okay? So you saved some energy, right? So this energy that would just be going down to the atmosphere, you are getting some economic value from it before being exchanged.
Is it simply just for reliability that like a turbocharged car motor does exactly the opposite? You try to get as much heat away from there as possible. Like you cool the air going in, and
Well, that cooling of the air coming in, I think, is another thing that we're going to be looking at in
Okay.
just a second.
Okay.
Because there are two ways of increasing the efficiencies. That one is another story. Here you go like, okay, now how am I increasing really the efficiency? You come in, when you draw this on a TS diagram, what happens? You're going from 2 to 3 to 4 to 1. This is what's happening in here. The network developed per unit mass is not altered by the addition of a regenerator, but since heat added is reduced, the thermal efficiency increases. Because remember, the thermal efficiency is equal to what? W cycle divided by Q in. Okay? By adding a regenerator, your Q in is actually smaller. You're dividing by something smaller, and therefore you get something higher. So, again, we're not going to be studying this anything, because now you're going to have a state X and a state Y that you have to worry about. Now, what is the effectiveness? The effectiveness, again, is depending on whether you have an actual versus reversible, but the regenerative effectiveness is defined as the ratio of the actual enthalpy increase, which is Hx minus H2, divided by H4 minus H2. Again, just in case you have to define that. Now we're going to skip this example. I mean, it's nothing really different than that first example of stuff, but it's got many different add-ons. Another way of looking at things is the modifications. The modifications of the basic gas turbine that increase the net work developed are multi-stage expansion with reheat and multi-stage compression with intercooling. Okay, that's where the cooling comes in. So, and these are obviously done to increase the thermal efficiency. Let's take a look at each one separately. The first one is similar to what we have seen for the vapor power cycle. What do you see here? You see that the expansion occurs in multi-stage. Okay? So instead of just going compressor, combustor, turbine, and then repeat the story, here we actually expand to an intermediate pressure, right? And then go back and then reheat first, right? You see, you go from 2 to 3. 2 to 3, what's happening between 2 and 3? Constant pressure, heat addition, and then 3 to A, what happened? We expanded to an intermediate pressure, isentropically. Then what happened between A and B? We added heat again at constant pressure, and then we expanded through the rest and then came back. So when you look at this, you go like, what is the difference between this and this guy? Do you agree that it's this little guy right there? That's extra area. And what is, by the way, what is this area here mean?
It's your work, right?
It's the heat or work. Yeah. Yeah, because it's a cycle, right? By adding this little thing, that means we have increased the work, right? If you increase the work, remember efficiency is work divided by heat in. So if you increase the work, that means you have increased the efficiency. Okay? So this is when you do it obviously through one expansion. Okay, that's another example. But again, the downside about this is how many states now do you have to analyze? 1, 2, 3, 4, 5, 6, kind of 7 almost, That's almost double the original number of states. Now the other one is, so we are doing this at the hot side, right? But at the cold side, the big question is it easier to compress cold air or hot air?
Cold.
Why is that?
Well, cold air is more dense already.
It's already more dense.
Oh, yeah.
All right. So if you look at, it says cooling a gas during compression is advantageous in terms of the work input requirement, because the net work output of a gas turbine can be increased by reducing the compressor work input. You see, these are connected in a way, but as this guy eats up uses up more work, obviously you're harnessing less work on the other side. So maybe one way to get the more net work is to kind of reduce how much this guy is using up. So it says this can be accomplished by means of a multi-stage compression with cooling. Now, here if you are doing what we call an adiabatic compression, and that means without losing any heat, I guess. And this one is as you compress with cooling. Remember, the cooling of a gas reduces what? Specific volume, right? And you know that the work is equal to the integral of PdV, right? So the integral of PdV, if this is P versus V, do you agree that this is kind of the area represents kind of work, right? So if you cool, right, you are kind of shaving off, so this is pictorially speaking, graphically speaking, you are shaving off some of the work, and therefore you will be getting more work on the other side. It says this can be accomplished by that the smaller area to the left of process 1-2, the smaller area here, indicates that the work of this process is less than for the adiabatic compression from 1 to 2 prime, which is typically what we consider to be, it's adiabatic, meaning it's isentropic, right? So cooling a gas during compression is advantageous in terms of work input requirement. Now we looked at what we were doing, the multi-stage expansion. Now here we do the cooling. Now if you do both of them, obviously you would be getting even better, right? You're getting benefits on both sides. It says, although cooling the gas as it is compressed would reduce the work, a heat transfer rate high enough to affect significant reduction of work is difficult to achieve in practice. A practical alternative to separate the work and heat interactions into separate processes by letting compression take place in stages with heat exchangers called intercoolers. Now, it's easily said than done when we say, well, cooling a gas and this and that. How do you achieve it, right? The way you achieve that is, again, by multi-stage compression. But you just don't do, just like in the previous case where we were doing expansion with extra heating, here we'll do extra, multi-stage compression with cooling in between, okay? That's kind of the idea. You compress here, you cool, that means you come in, do this and do that. You see, now you end up with an area that is less than the original area. See, conceptually it makes sense, but sitting there and trying to analyze this in detail is kind of an undertaking, because now you have, again, a bunch of cases that you have to worry about. And again, the goal in this class, in this chapter, is really just to know those three, but we do have to mention, at least what intercooling means, and this and that, and those. And the idea behind those is really to increase the efficiency. Again, I'm skipping these examples. Would you like something like this in the exam?
Please, no.
Even with an open book, I think it's it's crazy. So now, reheat and intercooling. Now we looked at each one of them. No, this is just for fun, just looking at it, and then we'll forget about it. We looked at reheat, right, initially, and then we looked at intercooling. Now, what if you have reheat and intercooling? Obviously, this becomes and this is, by the way, just two-stage compression and two-stage expansion. Okay?
What's a scenario where you would see this?
You're not going to see this like that.
Okay. I was
This
just
is all
thinking-
theoretical mumbo jumbo.
Okay.
So the reheat again. So when you look at the S diagram, remember you get this extra area here because of that, and then you get the extra work reduction on the compression side, and then when reheat and intercooling are used together with regeneration, then theoretically you will have a substantial improvement in performance of the process.
How substantial?
How substantial? Well, we're going to come to this. Not very much if you just do double. you know. Theoretically, you have to do at least 5 or 6 on each one of them, but then it becomes ridiculous. Is it worth it or not? The economics come into the play and this and that, and but nobody uses this as this, you know. So you almost have to have more than one, more than 2. But then you're increasing the number of moving parts in your stuff, right? If one of them messes up, even if the other turbine is working, obviously you have issues. See what I'm saying? You know? Okay, skip this one. Let me show you this other one. No, I think that was it, at least for this. So again, I didn't want to just skip that part without telling you what intercooling is and what reheat means, because it has some relationship to the exergy that we talked about before. Now we move on to another gas turbine that is used for aircraft propulsion. Now it's up there, right? And a good example is the turbojet engine. And gas turbines are particularly suited for aircraft propulsion because of their favorable power to weight ratio. And the turbojet is commonly used for this purpose. And the turbojet is defined, it has like 3, of course it doesn't look exactly like this, right? But it functions like that in a sense that you typically have a diffuser which brings in air, right? And then what happens here, why is this called a diffuser? Because obviously the area is increasing, right? As the area increases, so it brings so you got air that's coming in, and this phase in here is the gas generator, you know, which contains obviously the compressor, right? And it's got the combustion and the turbine, you know. All these 3 kind of one after the other, you know, comprise what we call the gas generator. And after that, obviously, you're going to get the products, gases out at a certain velocity, right? And then as the velocity conservation of momentum issues, you know, will create what we call the thrust. So on a TS diagram, you're going to get something that kind of looks like this, right? Some isentropic processes and constant pressure processes, okay? Again, the 3 main sections are the diffuser, the gas generator, and then because the diffuser, what the diffuser tends to do is slow down the air, right? Because you're coming in at high, at low, at a certain cross section, and then you decrease that, or you increase that. So the diffuser placed before the compressor decelerates the incoming air relative to the engine, and as the velocity goes down, what happens to the pressure? Do you remember there is a law that we've just been studying in fluids recently? Bernoulli, yeah. Bernoulli, as the velocity goes down, the pressure goes up, okay? So there is a pressure rise known as the ram effect is associated with this deceleration. Now the gas generator consists of those 3 components, which is the compressor, the combustor, and the turbine. The gases leave the turbine at a pressure significantly greater than atmospheric pressure and expand through the nozzle at high velocity before being discharged to the surrounding. And then, of course, the overall change in velocity of the gases relative to the engine gives rise to the propulsive force or thrust. So this is the basic principle of propulsion. So you're coming in with a certain velocity, going out with a higher velocity, right? So you gotta have some momentum, propulsive force that comes into the game.
I got a question. So if you took a rocket motor, right? Say your rocket motor in space makes 100 pounds of thrust. Well, in space, there's no atmosphere, so it literally is going forward or being propelled simply because of equal and opposite force, right? You got 100 pounds of thrust going this way, so it's going to go that way. If you took that same motor and put it in an atmosphere where there was a little bit of atmosphere for that thrust to push against,
Mhm.
how much does that lack or, or atmosphere play into efficiency? Or just, I mean. how
Well,
big of a
if
deal
you're,
is
if
that?
you're in the atmosphere versus less atmosphere, I guess, so you're talking about extra forces that you're fighting against, right?
Yeah.
It's just all forces after all, right? It's drag,
Yeah.
whatever, right? And if you're doing that, obviously you're, I don't know what you mean by efficiency.
Like, yeah, I
Because
guess
if you
I'm thinking about the question enough.
that means you'll be fighting not only
Yeah,
the
I didn't
drag
think
on the
about the
thing.
rest of the spaceship, so to speak.
Yeah.
That the air that the motor gets to push on is also pushing on the whole dang thing.
Mm-hmm,
So, okay, yeah.
Yeah.
Alright.
I mean, it's a more complex,
Yeah.
more complex dynamics going on there.
Yeah.
So again, how do you analyze? The big question is, how is this type of thing analyzed? It says, in accordance with the assumption of air standard analysis. Remember what air standard analysis means? The assumptions. Remember when we say that we forget about combustion and we say, hey, we're just adding heat, right? And and then the combustion gases are assumed to be following ideal gas law, et cetera, et cetera. So air standard, the working as is modeled as an ideal gas law. The diffuser, compressor, turbine, nozzle process are isentropic, and the combustor operates at constant pressure. So again, and this is just showing the, explaining just that TS diagram that we were talking about. You know, 8 to 1, 1 to 2, 2 to 3, 4, 5, etc., etc. And then we move on from there. Pressurized that occurs in the diffuser, isentropic compression, constant pressure heat addition, and isentropic expansion followed by an isentropic extension through the nozzle. Again, I'm not going to do this example here because we're not going to be, it's not kind of part of our thing in here. Uh, 910 combined gas power gas turbine vapor power cycle. When you have two power cycles that the energy discharged by heat from one is used in another, well, I don't know how much value this has, but we talked about this in vapor power cycles too, is that, excuse me, at each one of these power cycles, you always have to have a place where you are rejecting heat, right? So you could theoretically use that as being like an input to another power cycle here that is underneath. And so when two power cycles are coupled, so that the heat to the vapor cycle is provided by the gas turbine, which is called a vapor, which may be called a topping cycle. And this is actually when you combine two power cycles. One is vapor, and the other one is, this is clearly a vapor power cycle because it has what? The pump, right? Combustor, turbine, etc. So the heat addition is coming from there. And usually you do this because the combustion gases that come out of here are usually pretty done.
That's just to bleed heat.
Yeah, to bleed heat, you know. And in the process, you're going to say, hey, I'm going to get something out of it before it goes away. A couple more words about Ericsson, very few words about Ericsson and Stirling cycles, because this could take each chapter on its own. We talked about, earlier at least, that you could have increases in thermal efficiency through intercooling, reheat, and regeneration, as we mentioned before, right? there is an economic limit as to the number of stages that can be employed. And that was a question before, you know, how many are you gonna do? If two of them does create an improvement, I mean, it makes sense that if that 3 would do better, 4 will do better, 5 will do better, right? And then you go like, okay, now how many expansions, how many turbines I'm gonna stack one after the other? How many intermediate pressures I have to design? It says there is an economic limit to the number of stages that can be employed, and normally there would be no more than 2 or 3. Nonetheless, it is instructive to consider the situation where the number of stages becomes indefinitely large. This is like what mathematicians typically do when you do numerical analysis and you try to integrate a function. You break it into just a few points, right? And then you go like, yeah, that's approximately this. That's good enough, right? But if you want to be more exact, what do you tend to do? Well, keep breaking the darn thing into, double and double and double and double. And obviously, at some point, you're going to get closer to the real integral. But is it really worth it, right? Here, the theoretical exercise has been done to kind of figure out. Remember, this is the reheat stuff that we were doing before. So each one of them has to have a, you're coming down to another pressure, going and reheat, etc. This is the intercooling that's coming down, and this is just a schematic. So if you increase these many times, technically you would get what? It says here, the limiting cycle is called the Ericsson cycle as shown in B, okay? Ericsson cycle as a limit, it's not a true really cycle, it's just it's a limit of an ideal gas turbine operation using multi-stage compression with intercooling and multi-stage expansion with reheating and regeneration, okay? So when you do it like this, you go, that's a Stirling Ericsson cycle, let's analyze it that way. Another cycle that employs a regenerator is the Stirling cycle. Stirling cycle is kind of also called, maybe one of these days I'm going to bring a demo that's probably better than anything else.
Stirling engine?
A Stirling engine, yeah. I think I may have one at home somewhere,
Of course you would.
Yeah, I think it'll be a cool one to show. Because just looking at it like this doesn't make sense, right? It's a regenerator is the Stirling. It's called an external combustion engine. It's an engine that you probably just place your hand on like this. You're just adding heat, remember? And then you see the thing turning and turning, right? And then maybe you put it on ice, then it turns the other way. That's a cool little toy. If I remember, I'll bring it next week. Okay, so this cycle consists of 4 internally reversible processes in series: isothermal compression, constant volume, etc., etc. And again, this is what I meant to say earlier: is a practical engine of the piston cylinder type that operates in a closed regenerative cycle having features. It's called the Stirling engine, which is an external combustion engine. I'll bring this one if I still have it, or I'll have to order one. And now we got to that last section. Now, the last section talks about compressible flow preliminaries. Compressible flow, as you know, is a very compressible flow could be a class on its own, as you know. I took one at UW when I was there years ago. Just compressible flow. That's the only thing. So this is not going to do justice of being part of a chapter in Thermo to do compressible flow. We're going to do a little bit more on this on fluids when we get to fluids 2. But an interesting thing about this, when you talk about compressible flow, is that things happen in a very interesting ways. When you talk about subsonic flows, first of all, you know what subsonic flows means, right? That means that the velocity is less than, well, that means that the Mach number is less than 1, right? Or the velocity is less than the speed of sound. Okay? Now, if it's the case, as if you have an area that kind of increases like this in area, right? What happens to the velocity here? What happens, let's say, to, if you have here section 2 and section 1, you know that in this case, V2 is going to be, how does it compare to V1? It's going to be less than V1, right? And obviously the other thing is if you have that's a diffuser, obviously. No, that's not a diffuser, that's that's a diffuser. But if you have a nozzle, typically you will have here V2 is obviously greater than V1. And the big question about this is that when you have a Mach number that is less than 1, even if it's just air, when you have mass flow, remember the idea is that mass flow rate has to be constant, right? That's a fundamental equation of fluid mechanics, is that the mass has to be conserved. If you have a path of a fluid, right? An entrance and an exit, whatever goes from here has to come out from the other side. But what is the equation for mass flow rate? Is it equal to, what is it a function of, you think? It's a function of the density of the fluid. Depends on what kind of fluid is going through, right? It's a function of the area that it's going through, and it's a function of the velocity. Okay, so those three quantities are important, and then unit-wise, obviously kilograms per cubic meter, meter squared, meter per second. That should give you kilogram per second. Now, if rho is constant, what does rho constant mean? That the fluid is incompressible, okay? Incompressible. That means that this mass flow rate, because m dot is equal to a constant, right? Which equal to rho AV. Because rho is constant, this means that AV is equal to a constant. And in fluids, we call this the volumetric flow rate, right? So if the volumetric flow rate is really what dictates what these guys is doing, right? Here, the area 2 is greater than area 1. Here, the area 2 is less than area 1, right? And obviously, to have this constant, if one goes up, the other one has to go down. A funny thing happens when the flow becomes compressible. These laws are not applicable, particularly when the flow becomes supersonic and all that kind of stuff. So that's why the math becomes kind of very interesting in here. First, one thing about compressible flow preliminaries is that when you have a fluid flow coming in and changing direction, okay? What made this fluid change direction?
Geometry is the boundary.
That's
And
true,
height.
that is the boundary. But in terms of
pressure will make it change direction.
What's that? In terms of, well, think dynamics, think forces and velocities and this and that, right? The velocity is coming in this way, now the velocity is going that way. What caused that to change? It's a force. Remember, force always F equals ma, right? F equals ma, or right, which is m dv over dt type of thing, right? Now, you can look at a momentum change, and this one, for example, can be written as d of mv over dt, right? So the change in momentum with respect to time is really caused by force, or is related to force, if you will, right? So Newton's second law, time rate of change of momentum transfer into or out of a control volume accompanying mass flow is equal to m dot v, and we will develop this equation when we take the second part of the fluids class. In steady state, states that the resultant force F acting on the control volume equals the difference between the rates of momentum exiting and entering the control volume accompanying mass flow. So you get mass fluid, even if this one is just kind of a straight pipe, if you will, or a diffuser of a nozzle, right? If you have certain momentum coming in and certain momentum exiting, this change in momentum is creating a force. Okay. Now let's go into the idea of what a sound wave is. Okay. What is a sound wave? A sound wave is nothing more than a pressure disturbance. Right? It's a pressure disturbance that propagates through a gas, liquid or solid at a velocity c that depends on the properties of the medium. Okay, so how do you create something like this? Imagine you have a container that has just a big gas like this. You have a piston, and then you suddenly just tap on the piston very slightly. Okay? So you create this wave that propagates at a velocity c to the right. Now, this is this wave here is now, as it moves to the right, is dividing the fluid into two parts. On the left-hand side of the wave, what is the velocity? Well, the velocity is delta v, right? Because you caused that thing to go up. And because you increase the velocity, what happens to the pressure here? Slight increase in pressure. Do you agree? Slight increase in density. And also slight increase in temperature. Okay? And then on the right-hand side, here, anywhere, the fluid is still at a velocity in quiescent conditions. It doesn't know what's coming to it. It's still at pressure P, temperature T, and density rho. Now you have a wave that is kind of traveling from left to right. This is obviously a mathematical model. Now from a stationary observer is what he sees like this. He's seeing a wave that's moving to the right with the left-hand side, a fluid with its properties, on the right-hand side with nothing. Now suppose you bring this guy and then make him stand on the wave. Physicists like to do these types of things, you know? You go like, how am I standing on a wave, right? Because when he's sitting on a wave, now suddenly for him, this guy is not quiescent anymore, right? This guy is not at velocity 0, but this guy is traveling towards him at what velocity? Well, if he's standing on a wave that's going at velocity c, that means that this air here, which is not moving, is coming towards him at a velocity c. How about the air that was here at velocity, moving from left to right at velocity c, but now he's on a train that is moving to the right at velocity c. So how fast is this fluid coming towards him or going away from him? It's obviously the difference between the two. Okay? So, so let's look at this in an interesting way, because the big idea is that m dot is equal to a constant. Okay? All right? So, and you guys told me that this is rho times a times some velocity, right? So this is the basic start of any compressible flow thing, is that the mass flow rate is constant, but we do not neglect rho. Rho is subject to change also. Now, if I apply this equation on the left-hand side here, what do I get? Well, the density on the right-hand side is what? Rho. The cross-sectional area A is, I guess, A, right? And the velocity, from an observer's viewpoint, okay? So this is going to be rho A times C, okay? Rho here, the area A times C should equal to whatever is going on, see the control volume? At section 1, what do you have? Mass flow rate is rho AC, period, at this section. But at this section, what would this be? Well, you go like, oh, why is my density there? Well, my density is rho plus delta rho. The area is still A, right? Didn't change. And then, but the velocity is C minus delta V. Okay? So here you go and obviously expand a little bit this guy, right? So what do we get? Well, I guess we neglect the A's, right? And then we get rho C is equal to rho C minus rho delta V plus C delta rho minus delta rho delta V. If I were to expand this after simplifying with A, that's what I get. Now, why do you think, first of all, there is a rho C here, there is a rho C here, so this cancels out, this becomes 0, right? Equals minus rho delta V plus C delta rho. Why are we neglecting this term? Why are we saying that this is really small? See? Delta rho delta V equal to 0. Why would this guy be 0? Is it truly 0? No, because delta rho is finite, delta V is finite, right? But again, in engineering, you always have to look at orders of magnitude, right? If you remember the Taylor series expansion of a function, I don't know if that rings a bell or not. We have something like fx is equal to fx0 plus x minus x0 f prime of x0, right? Plus something like this, x minus 0 squared factorial 2 prime x0, oops, plus boom, 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 you know, just take more derivative and stuff. But if you truncate this series right here, this is just the definition of the derivative. When we say that f prime of x0 in calculus that it's the limit as x approaches x0 of fx minus fx0 divided by x minus x0. You guys remember this? That's a definition of a derivative, right? But it says the limit as x approaches x0. Because if it's not, that means you are only approximating the derivative. When we say this, that means we are neglecting these terms. Put in simple terms, this is what it is. If you have delta x equals, let's say dx, is equal to 0.001, let's say, which is 10 to the minus 3, right? So if you have another dx times dx, what would that be equal to? 10 to the minus 6, right? So do you think this guy can be neglected with respect to this? Do you think like 10 to the minus 6 is really small compared to 10 to the minus 3? Hell yes, you know, if you take the ratio of them, you find it's 10 to the minus 3. It's like 1,000th, you know, of that. So anytime you have, in engineering, anytime you have delta, that means it's little value, right? When you square, or when you multiply two things that are small, you get something even smaller. When you multiply by 0.1 by 0.1, what do you get? 0.01. See, isn't that smaller than the original two? That's the idea behind neglecting that term. So we come back in here, and if we ignore this guy and say it is small, that means that we have an equation that comes in like this, which can be simplified as simply delta V is equal to simply C over rho times delta rho. So the first equation of interest in here is that this change in velocity that we have created there is related to this change in density that was created here to the right face of the piston according to this equation. And this is just from on the basis of conservation of mass. Now, first equation. Now you go back and say, let me do the same thing, but apply it in here, but use here, this is this conservation of mass. What do you think in here is? This is that force is equal to m dot 1 v1 minus m dot 2 v2, right, from the previous slide, I think. M dot, sorry, it's the opposite. M dot 2 v2 minus m dot, in other words, a change in momentum. Okay? So if I were to apply this equation, which is Newton's second law, I have to apply it to here. Now look at this. What is the force acting on this face? You go like, what the heck is the force? Well, how is force related to pressure? Force is equal to pressure times area, right? So on this face, you have a force that's pushing this way from right to left, right? At a pressure times the area. How about here? What's acting? The force is in which direction? Remember, pressure always acts normal to a surface. So on here, the force will be directed to the right, and it's the pressure on this side, which is what? P plus delta P times A, okay? That's the sum of the forces, is equal to m dot times the V at the x, V2, which is this one, C minus delta V, minus m dot V1, which is m dot times C. See? This equation is merely the application of this. After you simplify again, PA, you probably will notice in here that you have PA minus PA that goes away, and you only end up with A delta P, right? But we already know that delta P is equal to rho C times delta V, right? So we come here with delta P times A is equal to m dot times VC, delta V, or rho AC times delta V. When you combine these two equations, by the way, this is what you end up with, is that this velocity that the wave is traveling at is related to the change in pressure and the change in density according to this. And just for your information, this is not gonna be in any exam or any stuff, okay? But that doesn't mean you ignore it, right? Maybe in the fluids one next time.
We can ignore it for the fluids class
Oh,
too?
no, for the fluids, it won't be ignored. That's why a lot of people hate the compressible flow, because you can only explain compressible flow by math. There's no other way, you know? So we come up with this, and then in addition to this relationship that we just talked about, which is C is equal to delta P over delta rho, we come back and say, hey, what is the speed of sound in an ideal gas equal to? Then you have to remember the kinetic theory of gases, which is that the speed of sound is actually a function of the square root of the temperature of the gas, you know, according to this. C is equal to square root of kRT. Now, we also define the Mach number as simply being the velocity divided by C, right? And when m is greater than 1, the flow is supersonic. And this is the sonic velocity, C, by the way. When m is less than 1, the flow is subsonic. When m is 1, the flow is sonic. And okay,
So you're using C for both the speed of light and for the speed of.
well, the book here uses it. Yeah, typically it's used for the speed of light. You're right. You know, C. Here they're using it for the speed of
Subsonic.
sonic, the speed of sound. Yeah. Yeah, that's yeah. They run out of letters to use.
There's 6 of them.
Look at V. You know
I know.
what V is used for.
And how many Q's are there?
Or how many Qs? How many? Yeah, yeah.
Meet these,
I'm with you on that one.
Oh.
There's only one that matters though.
Upper end or something.
All right. So when dealing with compressible flow, it is often convenient to work with properties evaluated at a reference state. So this is another the kind of a last part of this. The stagnation state is the state of a flowing fluid with attained, if it will, decelerated to zero velocity isentropically. In other words, without losing any energy at all. Okay. So in this case, obviously, the stagnation enthalpy is h plus v squared divided by 2. And coming back, and we got 2 more slides. And this is just to get to one equation that's just going to define what we were talking about earlier. So we determine the shapes required by nozzles and diffusers for subsonic and supersonic flow. Okay, and the whole idea in this Thermo, at least textbook, is really just to show that in supersonic flow, things happen opposite than what happens in subsonic flows. So this is accomplished using mass, energy, entropy, momentum principle together with property relationships. We study how the flow through nozzles is affected as conditions at the nozzles are changed. Now, this is again, we got I think two or three more slides to go through. So for a constant volume, enclosing a nozzle. If somebody writes rho AV equal to constant, what does this mean? Remember what rho AV is, right? That's the mass flow rate. Mass flow rate is constant. So how many variables are in this function? 1, 2, 3, right? 1 is then rho, which is potentially could change, A could potentially change, and V could potentially change. Now, if I want to take what does this one mean, by the way? D of rho AV. What does D mean? Differential. What's the differential of a constant? 0. So the differential of a constant is 0. Then you can come back from your multivariable calculus, right? When you take rho AV is equal to a constant, right? D of rho AV is equal to 0. then what does D of rho AV mean? Well, remember you take, it's AV, remember it's multivariable, so you have to take each one separately, right? By considering the other two being constant. So for example, it's going to be AV times D rho plus, now I assume that A is changing, but rho V is constant. Now I assume it's V that's changing and rho A is constant. Do you agree that this is the same thing as that? Okay. Now, obviously, in this case, what I could do is I could divide this entire thing by rho AV, just to get kind of a cleaner equation. If I divide this by rho AV, what do I get? See, AV cancels out, so I get D rho over rho plus, how about here? It's rho V that cancels out, plus dA over A, and then here plus dV over V is equal to 0. Okay. So you get an equation of this form, okay, differentiated. After you divide both sides by rho AV, you get this equation. Then you go like, okay, what am I going to do here? I have two states, you know, and I'm going to use the enthalpy at state number 2 is equal to the enthalpy stagnation enthalpy of state 2 equals stagnation enthalpy of state 1. Remember, stagnation enthalpy is H plus V squared over 2, you know, and which in general H plus V squared over 2 is constant. That means, again, if I take the differential of this, what do I end up with? See, it's all math, unfortunately. V squared over 2 is equal to 0 because this is constant, right? So this becomes dH plus d of V squared over 2. What is d of V squared over 2? It's going to be, see, 2 and 2 cancel out, right? It's plus V dV equal to 0. Or dH is equal to minus V dV. So all this differential exercise is continued, right? And then using the good old TDS equations that we talked about before. But let's just go to the last slide in here. That equation, this is what I was getting at. I just didn't want to show you this without the source of it. So this equation here has been derived using conservation of momentum, conservation of mass, conservation of energy, and what does it show? It shows how the area changes and how, what does V represent? The velocity changes for different Mach numbers. Okay, so this equation is valid whether you are in subsonic, supersonic, or whatever. Okay, so if you look at it in a subsonic way, in fact, I'm rewriting it in here. dA over A equals negative dV over V, 1 minus m squared. This equation's above, the above equation shows how area must vary with velocity. That's the whole idea. How area must vary with velocity. And you have to identify about 4 cases. First, if it's a subsonic nozzle, remember what a nozzle is, right? Subsonic. Subsonic nozzle, that means that m is less than 1 because it's subsonic. If I look at this equation, if m less than 1, this term would be what? Positive or negative? Positive, right? That means that dA will be proportional to what? Negative dV. Does that make sense? because this is positive, right? That means that if dA is positive, dV will be, better be negative, right? If dA is negative, then dV better be positive. There's no other way, right? We're not talking about how much by how much, we just know the signs have to be different. In other words, the velocity and the area have to go different ways. So, dV here, in this case, because it's subsonic, what happens to dV? If you want the velocity to increase, right? If dV is positive, right? Then dA better be what? Negative. That's why in order to have a velocity increase in here, your area has to go down. Okay? So the duct, you can say that the duct is converging in the direction of the flow. Okay? How about if you look at supersonic nozzle? Okay? Again, something like this. Supersonic nozzle, this term is m is greater than 1, this guy becomes negative. That means that dA will have the same, so the negative and the negative cancel out. That means that dA is same sign as dV, right? That means if, like for example, if dV, if you want the velocity to increase because you are thinking it's a nozzle, right? dV is greater than 0, then obviously dA better be greater than 0. So the way you're going to have this is that the duct will diverge, not converge. So this is not a diffuser. In subsonic it is a diffuser, but in supersonic it is a nozzle. See, it changes stories.
So that's why the turkey feathers on like a military aircraft when it goes.
Exactly.
fires up the ocean.
Yes. So in here, obviously you have the A2, the dV is greater than that, and obviously it also happens to the diffuser, you know, in different stories. Right? The diffuser here is going to be like this, right? But in this case, it's going to be more like this, right? So a lot of different funny things happen when you are in supersonic flow. In fact, it says as Mach number of unity can occur only at a location in a nozzle or diffuser where the cross-sectional area is a minimum, particularly when you change from subsonic to supersonic, right? Because subsonic, obviously, Mach is less than 1, supersonic is greater than 1, so you go like, hey, you know, to have a velocity that is equal to the, when m is equal to, when m is equal to 1, essentially, you have that dA is equal to 0. That means that you have an area where it kind of flattens out, if you will, right? So Mach number of unity can only occur at a location on the nozzle or diffuser where the cross-sectional area is a minimum because you have dA is equal to 0. This location is minimum, is called the throat, right? It's either here or there, right? Going from subsonic to supersonic or from supersonic to subsonic, you know, for either one of those cases. And that it concludes actually my chapter in here. So when we meet, I guess you wanna start the refrigeration today, or defer that? Taki is saying, please do. So when we meet next time, we will. Actually, we don't have a lot left in this class. We have the refrigeration, then we have the TDS. We have mathematical equations that create the tables, and then we have a little bit of cyclometry at the end. So think we are on schedule. I checked my syllabus today. I think we are on schedule, so I'm not too concerned at all, okay? And the refrigeration, by the way, you're just gonna learn again 1 or 2 cycles on that one. Maybe 1, that's critical. And